All right, so to do the last little bit of this proof, to show that 3 colorability is NP-hard, we're going to show that if we had the ability to solve 3 colorability problems in polynomial time, then we could solve 3 SAT problems in polynomial time as well. And so what we need to be able to do to show that is if you walk up to me with any 3CNF formula, I can quickly turn it into a 3 colorability problem, which is going to be a graph, such that that graph is 3 colorable if and only if the original formula, the 3CNF formula that we're given, is satisfiable. So CNF here just means conjunctive normal form. It's just that form that I showed you before where the formula is the AND of a bunch of clauses, and each clause is the OR of 3 literals, and each literal is either a variable or its negation, not that variable. So you walk up to me with a 3CNF problem, I turn that into a 3 colorability problem that can be colored if and only if the formula is satisfiable. Sounds like an interesting challenge. So let's get to it. What we're going to be doing is building a graph. We'll start off by creating some nodes with one node for every possible literal in the formula. So that's the k different variables. Oh, let's say this. Just to be concrete, this formula that we come to has k variables and s clauses. Now we're going to add 3 more nodes, and we'll call them true, false, and slack. And we're going to connect up the nodes initially as follows. Each literal will be connected to slack, including true and false. And we're going to connect true and false to each other. And what that means, because there's a little triangle here, and we're trying to see whether or not it's 3 colorable, the only way that this thing can be 3 colorable is if these 3 are given 3 different colors. So just for concreteness, let's say that the color that slack gets is red, the color that true gets is blue, true blue, and the color that false gets is black, black, false one. All right, so the graph that we have so far has the property that each of these literals is going to have to be colored either true or false, blue or black, if we're going to 3 color the whole graph. So that's good. That kind of makes it seem like they're actually getting truth assignments. We have to be a little careful though, because literal V1 and literal not V1, they can't both be true and they can't both be false. But that's an easy thing to fix in a graph colorability problem. We just connect them with an edge. So if we add one edge for each variable, connecting the pair of literals that can't both be true and both be false, now what happens is the only way that we can 3 color this is if each variable is given blue for either the variable and black for its negation, or black for the variable and blue for the negation, and that's like a truth assignment, a true-false assignment to that variable. So any possible truth assignment corresponds to a 3 coloring, any possible 3 coloring corresponds to a truth assignment. So far we're in really good shape as far as capturing the idea, the physics of a SAT problem.